Hello. I woke up early this morning, and instead of going back to sleep, I thought it would be an amazing idea to use some extra time to record one of these things. So, this is the midterm one section of the fall 2018 final exam for MA266, and we can actually do, we can do a little over half of this exam, so more than usual. So we'll be here for a little bit. Question 1. Find the explicit solution to the initial value problem given here. Well, it's pretty easy to see how this differential equation here is separable. We're going to multiply y over, multiply dt over, and integrate. So we will end up with the integral of y dy being equal to the integral of t over root 1 plus t squared dt. We're going to do a u sub on this side, where u is equal to 1 plus t squared. Du is equal to 2t dt. So integrating on our left side, we're going to get y squared over 2 being equal to 1/2 integral of 1 over u, 1 over root u, which is u to the negative 1/2 du. This integral is going to give us y squared over 2 equals 1 plus t squared plus c. Okay, so let's multiply everything out. Let's put this in an explicit form. We'll get y squared is equal to 2 plus 2t squared. And I'm not going to write 2c because that's just another different constant, so I'll keep it as c. And then we're taking a square root. But importantly, we see that y of 0 is negative 2. So we are going to want the negative side of this square root. Oh, and look what I did. When I took this integral, I forgot that there's still a square root. Because this, integrating here, this will take negative 1/2. It'll take it up to u to the 1/2. Then we'll multiply by 2. So that's why we lost this constant here. But I did neglect that. So 2, 1 plus t squared to the 1/2. There we go. Okay, so that should be our formula there. We can already start going in and getting rid of some of these answer choices. B, we know to be false because that's not an explicit form. We need it in the form y equals. And let's see. A is wrong, and so is C. We only want the negative section. We know that for a fact. So let's plug it in, and let's plug in x equals 0 and find our value C. And I have a pretty good hunch that we're going to get D as our answer choice. So plugging in our values, negative 2 for y equals negative root 2 times 1 plus 0 to the 1/2 plus c. This is negative 2 is equal to negative root 2 plus c, so c must be 2. So our answer for number 1 is D. Initially, a tank, okay, I'm not reading all this, but the formula that you just have to bash into your skull until it sticks is dq dt plus r0 over v of t multiplied by q is equal to ri ci. I have no mnemonic, no anything for memorizing this. I think if you just do a couple of these problems and at the top you force yourself to write this out every time, I think it'll stick pretty quickly. So knowing that, all we have to do is fill in the blanks. We know that RO is the rate of outflow from the tank, and RI is the rate of inflow of contaminated or sugary or salty water, whatever they're. In this case, it's sugar that's flowing into the tank. We also have V of t, which is the expression that tells us how the volume of the tank is changing over time. And Am I missing anything? Yes, I am. Ci is our concentration of whatever solute is coming in with our solvents. In this case, it's sugar and water. Okay, so we can start filling these in. C of t, they're telling us, is 2 plus cosine 3t. 2 plus cosine 3t. Okay. We see that v of t is initially 100, so we can go add that there. And we also have an initial condition here at q of 0. So sugar at time equals 0 is going to be 10 kilograms. And that may be, it's actually not important for this question, but if we were to actually solve it, we would take that into account later on. Okay, we have sugar water flowing into the tank at a rate of 2 liters per minute, so rate in is 2, and it's flowing out at a rate of 5 liters per minute. So volume initially is 100, but since we have 3 more liters flowing out than are flowing in every second, we have to subtract 3t. So for every unit t, we lose 3 liters of volume. Okay, and we're pretty much done because all we have to do is plug these values in. dq dt plus r0, which is 5 over 100 minus 3t. Q is equal to 2 times 2 plus cosine 3t. And if we look through our answer choices, I'm going to get rid of the ones with the signs. With sign in here, we know that that's incorrect. And it looks like they've moved this term over to the right side in all these answer choices. So we should have negative 5q over 100 minus 3t, which is answer choice B. It matches everything we've set up. And they're kind of doing a trade-off here where they make you set up a little bit more of a complicated, expression. They wouldn't have us solve this cosine 3t kind of shenanigans. I think it would turn into a very ugly integral. But in exchange, all we have to do is set the thing up, which is pretty nice. Question 3, find the implicit solution to the following initial value problem. So the minute you see something as disgusting as this, in this form, where we have some function, and just to save time, we're calling this function m, plus some function x times y prime equals 0, and they look relatively similar, the first thing that should come to your mind is, okay, there's a pretty good chance that this equation is exact. And the way we check that is we see if the partial derivative of m with respect to y is the same as the partial derivative. We're not calling this x, we're calling this n. I'm not sure why I said x. The partial derivative of n with respect to x. So my over here is going to be xy, negative xy sine of x squared plus y squared over 2. And over here, nx is going to be negative xy sine x squared plus y squared divided by 2. Okay, so we know that our equation is exact. We can now integrate m dx, and when we do that, we will get we're integrating. We will get sine x squared plus y squared over 2. And then on the other side, when we integrate n dy, we will get y squared plus sine x squared plus y squared over 2. And so since both of these functions come from one overall parent function where m is just the partial derivative of that function with respect to x, and n is the partial derivative of that function with respect to y, we can only count one of these signs. Just as in, if we have an example here, if our potential function, kind of going back to a little Calc 3 stuff, if our potential function, say p of xy, is x squared y, and then we have px 2xy and py being x squared. If we had both of these and we were trying to find the function that they came from, taking an integral for p of x, well, both of these integrated will give us x squared y. But then if we add them together, we would get 2x squared y, which is clearly not what our original function was. Okay, so all that's to say that our function overall is let's see, letters are hard. Y of, well, it's actually, sorry, I need to calm down. This is not in explicit form. So our overall function is going to be sine x squared plus y squared over 2 plus y squared is equal to our constant c. Now all we have to do is apply this initial condition, and we'll have a solution. So it looks like this will evaluate to sine pi over 2 plus pi is equal to c. Sine pi over 2 is 1, so c will be 1 plus pi. 1 plus pi, or pi plus 1, as they have in option E, which is correct. Question 4. Let's find the implicit solution to this initial value problem. Whenever you see, if they explicitly put a y over x, and especially if they have this kind of expression over here, where you're seeing something that would be very, very difficult, if not impossible, to separate normally by separation of variables, it's a good plan to use our substitution. V equals y over x, and we know that this will we can replace all of our y over x's with v, but we can also replace y prime with dv dx times x plus v. So dv dx x plus v is equal to v, because y over x is there's our substitution there, and we'll take all both the numerator and the denominator in this guy and divide it by x. So we'll get plus x over x, which is 1, plus 2 y over x, which is v, plus x over x, which is 1. Perfect. We can quickly subtract a v from both sides. That will get rid of both of those. And let's see what we can do here. Let's divide dv over times 1 over dv, and then flip both sides. So this will turn into 1 over x dx, and that's ready for integration, and 2v plus 1, sorry, 2v plus 2, distributing that 2 out dv, and we can integrate there as well. And I'm actually gonna flip our sides back order-wise, just so that we get the plus c on the side that we're used to. This integration will give us v squared plus 2v is equal to ln x plus c. We can replace our y's and x's. We will get y squared over x squared plus 2y over x is equal to ln x plus c. Let's multiply all terms by x squared. Y squared plus 2xy is equal to x squared ln x plus c. And if we apply our initial condition, we should be done, even though at this point we could choose this answer right here, because that's the only one that has the 2xy that we're expecting in our answer choice. So let's plug in y of 1 equals 1. That's 1 plus 2 times 1 times 1 equals 1 times ln 1, so 0 plus c. And so that gives us that value for of 3 for c. And it looks like over here I forgot, when I was multiplying everything by x squared, to multiply c by x squared, but that's a mistake that we can catch now. Okay, so for our answer is c. Question 5, let's find the approximation of y at 3 using Euler's method with a step size of h equals 1. And it looks like we're starting at t is equal to 0, and we're told that that initial y value is 2. So our approximation of y of 1 is approximately 2 plus our step size, which is 1, multiplied by y prime evaluated at our current our current initial condition here. So that will be cosine of 0, which is 1, times y of t, which is 2, minus t, which is 0. So this will be 2. So overall, we have a new y value of 4. So now we're looking at y of 1 is approximately 4. And so our approximation for y of 2 will take this into account. We have 4 plus our step size, 1, multiplied by, let's see, the cosine of pi, which is negative 1, times y, which is 4, minus t, which is 1. So this will be 4 plus negative 5, or negative 1. So y of 2 is approximately equal to negative 1. And finally, y of 3 will be approximately equal to that previous y value, so negative 1, plus our step size, I'm not even going to write it anymore, it's just 1, multiplied by, let's see, well, t is equal to 2, so cosine of 2t will give us 1, times y of t, which is negative 1, so 1 times negative 1, minus t, which is 2, so minus 2. So we have negative 1 minus 3, or negative 4. So 5, our answer is B, which is correct. It's important, even if your step size is 1, just to get in the habit of writing these in, because when they switch it up on you and your step size is 1/2, or they also like 0.1, if you drop one of those, you'll have a bad time. Okay, 6. Let y of t be the solution to the initial value problem given here. So whenever we see anything tacked onto y prime in any of these first order differential equations here, we want to divide that out. So y prime is equal to, y prime minus 2 over t y is equal to t cubed. Perfect. So this is exactly the form that we like for the integrating factor. So we can raise e to the integral of negative 2 over t dt, and this is equal to our integrating factor rho. This is the same thing as e to the negative 2 ln t. We can bring that ln t down as just a t and get rid of the e, and we're left with t to the negative 2. So moving along, skipping a couple little steps, y of t is equal to 1 over rho, so t squared times the integral of q of t times rho of t, so t cubed times t to the negative 2 dt. This will simplify down to t dt. Okay, we have y of t is equal to t squared times the quantity t squared over 2 plus c. We can fill in what this c is by applying our initial condition. We have 0 equals 1 times 1 over 2 plus c. And so c must be negative 1 over 2. c equals negative 1 over 2. So we can fill that in. And they're asking us for y of 2. So finally, y of 2 is equal to 2 squared, 4 times 4 over 2 minus 1/2. So that is 4 times 3 over 2, or 6. Question 7. Which of the following is in the set of unstable equilibrium solutions of this equation here? So first of all, we need to identify what our solutions even are, our equilibrium solutions, and these will just occur when y is equal to 0. So the roots of this guy right here, you could think of them as the solutions for where y prime is equal to 0. So we see that y is equal to 0, y is equal to 1, and y is equal to -2. And this actually has a multiplicity of 2, but that will not come in. That will not really matter for us. So let's set this up. I'm going to make a nice little number line. We have going all the way from -infinity to -2, up to 0, up to 1, and then all the way back up to positive infinity. And all we have to do is see whether our derivative or our y prime is positive or negative in these sections, and we can identify the behavior around these points. So let's say we choose, and I'm going to get rid of these because we already have, this is a little bit redundant. Let's say if we choose y equals 1/2, then we'll have, and I'll put that in here, 1/2 times 1/2 minus 1 times 1/2 plus 2 squared. That's going to give us a negative number, so that's less than 0. And so we'll stick an arrow pointing down there. What about y is equal to 2? 2 times 2 minus 1 times 2 plus 2 squared is greater than 0, so that gets an upward arrow. What about -1? -1 times -1 minus 2, that's not a 2, that's a 1, times -1 plus 2 squared. This will give us a negative number times a negative number times a positive number, so that's another upward facing arrow. And then finally, what about -8 times -8 minus 1 times -8 plus 2 squared? That will also be an upward facing arrow. So the only unstable equilibrium solution we have, aka a solution where our answer is 1. So if you started a solution curve at 1.0001, it will flow up and away from 1. And if you start a solution curve at 0.9999, well, those got progressively worse. Our solution will flow back away from 1 towards 0. So we would call 0 a stable equilibrium solution. -2 is a semi-stable equilibrium solution, and 1 is an unstable equilibrium solution. So 7, our answer is B. Let's find the solution of this initial value problem right here. So right off the bat, we're seeing sines and cosines in our answer choices. We're kind of thinking that this might turn into some complex valued solutions, some complex conjugate solutions, and we can figure this out by setting up our characteristic equation, which will be r squared plus r plus 5/4 is equal to 0. Let's apply the quadratic formula, and I'll write this out explicitly. Actually, where a is equal to 1, that's our coefficient there. B is equal to 1, and C is equal to 5/4. So negative b, so -1, plus or minus the square root of b squared, so 1 minus 4 times a times c, so 1 minus 5, all divided by 2. This will give us plus or minus 2i, and we can divide this 2 out. So we know that we can set up our solution in the general form. Y of t is equal to c1 e to the at cosine bt plus c2 e to the at sine bt. And just to be clear, b is our coefficient on I, where a is the real part of our solution. So plugging these in, y of t is equal to c1, which we still don't know, e to the negative t over 2 cosine t plus c2 which we also still don't know, e to the negative t over 2 sine t. And at this point, we can get rid of a lot of answer choices here. In fact, we can get rid, and I didn't realize this when I was looking over this before, we can get rid of all of them because none of them have our correct values for A and B in there. The only one that's close is A, but it has positive t over 2 when we know that it, in fact, should be negative. So 8, our answer is E, but let's go back and actually find these constants. We're going to have to take a y prime of t, and this is going to get really tedious really quick. C1 times negative 1/2 e to the negative t over 2 cosine t minus, I'm not going to do this. Or maybe I am. We'll see. This is going to suck though. E to the negative t over 2 sine t. Okay, and then second half plus negative c2 times negative 1 over 2 e to the negative t over 2 sine t plus e to the negative t over 2 cosine t. Okay, my God. So when we plug in y at 0, we should get 3. So 3 is equal to c1 e to the 0 cosine 0. So that will be just c1 plus c2 e to the 0 sine 0, which will be 0. And so that tells us, we're on the right track. We found that 3 for C1. And then finally, for y prime at 0, it should be 1. So 1 is equal to 3 times all of because we found out our value for C1, so we might as well plug it in, times all of this stuff. So negative 1/2 e to the 0 cosine 0 is negative 1/2. This bit, anything with a sign in it is going to go to 0, plus C2, this bit has a sign, so we can disregard it, times 1. And we see that 1 equals negative 3 over 2 plus C2 is the same thing as 5 over 2. So almost didn't do that. I'm glad I went through and did the work, and we've proven why that answer choice is correct. But I do like how as long as you've got the background work done, if you've set everything up correctly, they don't really, in this case, they don't force you to go through the motions, which is always nice. Question 11. Let's find the general solution for this differential equation here. We can make a characteristic equation, not y. R to the 4th plus 5r squared minus 36 is equal to 0. This is the same thing as r squared plus 9, r squared minus 4. And so these roots are going to be, plus or minus 3i and plus or minus 2. And I'm getting plus or minus 3i from this expression, r squared is equal to negative 9. So r is equal to plus or minus root negative 9, which is plus or minus 3i. And so just like in our last problem, we can set up all of our solutions here. We know that this real part right here, these are two separate solutions, the set of real solutions here will give us y of t being equal to c1 e to the 2t plus c2 e to the negative 2t t. And then for our plus or minus 3i, we are going to have plus c3 e to the at. Well, in this case, a is 0. You can think of this as 0 plus 3t, where this is a, this is b. So that e term will just simplify down to 1 cosine 3t plus c4 sine 3t. And so if we look through and, if we look through and cancel out all of our irrelevant answers, it looks like we've landed on option D for 11, which is correct. And here we go. It looks like there is one more question we can do. Question 13. The solution of this differential equation, one solution is y1 equals x. Another solution is some multiple v of x, where v is some other function of x here. And it's our job to find that, and we're going to use a nice little equation for reduction of order here. It says that y2 of x is equal to y1 of x times the integral, we need a really big integral for this one, of e to the negative integral p of x dx, all divided by y1 of x squared dx. Yet again, I have no particular method for remembering this one. In fact, I learned it yesterday to give you a little bit of perspective. But hopefully just, doing these things over and over again, sometimes it'll stick. So we need to figure out what our p of x is. That's going to be, coming from our equation that's in the form y double prime plus p of x y prime minus q of x y, plus q of x y is equal to 0. So we're going to have to divide out this y cubed. So y double prime plus 1 over x squared. Did I say y cubed? X squared minus 1 over x cubed y prime is equal to 0. Sorry, that was a very sloppy right there, but we can see that our value for p is 1 over x squared. We also know that our value y1 that will go here and here is x. So let's start setting this up. y2 of x is equal to x multiplied by e to the negative integral of 1 over x squared dx, all divided by x squared dx. So the integral of 1 over x squared dx is negative 1 over x. Combine that with the negative that we already have out here, and we get 1 over x. And we can actually do a u substitution here. If u is equal to 1 over x, du is negative 1 over x squared dx. And so applying that, we get y2 of x being equal to x multiplied by the integral of e to the u, negative e to the u, du. And this is perfect because our integral will give us y2 of x is equal to x times this function v that we're looking for, which is negative e to the u. But really that negative is just, plus c. Don't want to forget our plus c. And this u is actually 1 over x plus c. And since the only thing that we're looking for is the function that we're multiplying into x that's also a function of x, this guy we will call v. So v is equal to e to the 1 over x. And I hope that you can see how because all of our set of solutions, or all the linear combinations of this solution with y1, this both this negative sign and this plus c are irrelevant. So our answer is e to the 1 over x is the function v when multiplied by x gives us y2. So 13 is e. And I I don't know if there's a good way to remember this reduction of order formula. And I really hope that my professor will let me use it on the exam instead of applying the really annoying substitution. But okay, we can't do any more of these questions, so yeah, we're done. Hopefully this was helpful.